Hello, so in this video I'm going to talk about how we can find a particular set of fundamental solutions, and I'm going to talk in just a moment about what that actually means. Okay, but let's suppose I have this second order differential equation and I want to find my solutions of this second order differential equation. Remember, I seek a solution of the form y equals e to the rt. So first things first, I'm going to write this out as a Okay, I can't do any reduction of order or anything like that because the thing which is missing, okay, I've got a qt missing, I've got my function involving t missing, okay, I haven't got any t's involved, it's just 0, but I've also got a y1 missing, so therefore I can't really do anything interesting with that because I've got two things missing effectively. So I'm going to just have to solve it directly. It's not that difficult, I'm just going to have to form a characteristic equation. So this characteristic equation of this is going to be r squared minus 1 equals 0. Okay, and I'm going to find my root. So this is the difference of two squares, right? So this is r minus 1 times r plus 1 equals 0. So therefore r1 is equal to 1 and r2 is equal to minus 1. Okay, remember I seek a solution of the form y equals e to the rt. So let's say that y1 is e to the r1 times t and y2 is e to the r2 times t. Well, r1 is just 1, so it's just 1 times t, which is just t, and r2 is just going to be minus 1, so it's just going to become minus t. So y1 is e to the t, and y2 is e to the minus t. Okay, so I want these two solutions to effectively satisfy each of these initial conditions. That's what I'm after. I'm after a particular set of fundamental solutions. If you like, I'm being picky. Okay. Well, actually, let's first of all verify that these two solutions are in fact fundamental, and I can verify that by the Vronskin, because of course the Vronskin will determine whether they're fundamental or not. I want basically the Vronskin is non-zero. So in other words, I want the Vronskin is non-zero. So therefore, I want to verify that they are fundamental. I can verify that quite easily. So take the Vronskin of that thing. So it's the Vronskin is y1, y2, and the derivative, so y1 dash and y2 dash. So y1 dash is going to be e to the t, and y2 dash is e to the minus t. Okay, e to the minus t. So then I'll take the determinant of those two things. So I've got y1, so e to the t, y2, e to the minus t. I've got the derivative, e to the t, and minus e to the minus t. Okay, this is minus e to the minus t. And take the determinant of that two things. So I end up with e to the t multiplied by minus e to the minus t, minus e to the t times e to the minus t. Okay, and take the determinant of that, so I end up with minus e to the, well, this is going to become e to the t times e to the minus t, so that's just going to become e to the 0, right? Okay, so that's just going to become 1, right? And this thing in here is going to be minus e to the t times e to the minus t, so that just add the powers together, so therefore that's going to become e to the 0, which again is just going to become 1. So it's going to become minus 1 minus 1, that's going to become minus 2, and obviously minus 2 is not equal to 0, so therefore I can verify that y1 and y2 are in fact fundamental just by using the Vronskin. Okay, so I've verified that I've come up with fundamental solutions. I have come up with a fundamental solution. Okay, y1 equals e to the t, and y1 and y2 equals e to the minus t. They are fundamental. But I want a particular set of fundamental solutions. I want to be fussy. So in other words, I want these to satisfy these initial conditions. I want a set of solutions that satisfy these initial conditions. Okay, well, let's just verify that they do satisfy the initial conditions. So basically what I'm saying here is that y1, when I put 0 in, I should get 1. So when I put 0 in here, I should get 1. Well, I do get 1. That's right, I do get 1, so that's fine. Okay, then again, when I put 0 into, so when I take the first derivative and I put 0 into the first derivative, I should get 0. Well, I don't, I get 1. So therefore, this is wrong. Okay, I haven't got a set of solutions that satisfies this sort of first derivative is 0, so I haven't got a set of solutions there. Okay, let's try the same for the second solution. So in other words, when I put 0 into my second solution, 0 in here, I should get 0. I don't. I get 1. So therefore, that's wrong. And therefore, and also when I put 0 into my second solution differentiated, I should get 1. Well, when I put 0 in here, I get minus 1. So I don't get that set of solutions there. So in other words, what I end up with is that when y1 equals e to the t, and y2 equals e to the minus t, they don't satisfy this set of initial conditions. So it's not this particular set of fundamental solutions I want. what do I mean by particular? Well, just imagine you go into a shop and you want to buy something. You want to buy a particular type of thing. Okay, you've got an option of, say, like if you want to buy, say if you want to buy a bag of crisps. Okay, you want a particular brand of crisps. So, for example, you want Walkers. Okay, you don't not just any crisp will do. You want Walkers. You want a particular set of crisps. Okay, it's exactly the same thing here, except these are my fundamental solutions. So I've got a set of fundamental solutions here. Okay, fundamental solutions which satisfy the second, the second order differential equation. I have got a set of fundamental solutions here. Okay, but they don't satisfy these initial conditions. I want a particular set of fundamental solutions that satisfy these initial conditions. Okay, so I want a particular set, I want a particular variety of fundamental solutions. Okay, now I've just verified that these don't verify these fundamental solutions. So therefore, I need to come up with some solutions that do verify these initial conditions. I want a fundamental solution that do verify these initial conditions. Okay, so therefore, if I just say, well, okay, y1 and y2 don't satisfy these solutions, don't satisfy these initial conditions, so I want a new set that do. So let's call it y3, and I want to form a y3 and a y4 such that y3 when evaluated at 0 is 1, y3 when evaluated at 0 is 1, and the derivative of y3 when evaluated at 0 is 0. Okay, and also I want that y4 when evaluated at 0 is 0. Okay, and the derivative of y4 when evaluated at 0 is 1. Okay, so therefore I've formed a new set of solutions. Okay, so y3 and y4 that do satisfy this. This is what I want to find. I want to find a new set of solutions that do satisfy this. Well, I can come up with a new set of solutions based on my old solutions, right? Because I can just say, well, y3 is just some constant, let's say c1 times e to the t plus c2 times e to the minus t. Yeah, it's just going to be y1 and y2. Okay, and likewise, I can say that y4 is just another set of constants. Let's say k1 times y1 plus k2 times y2. Okay, so if now I just replace y1 with my y1 up here, so e to the t, and y2 is e to the minus t, so e to the t and e to the minus t. So therefore, this is my new set of solutions. And I want these a new set of solutions in such a way, I want to form these new set of solutions in such a way that they do satisfy these initial conditions. So in other words, the thing which is going to determine, it's going to make them satisfy these initial conditions, are these constants. These constants are going to make them satisfy this initial conditions in my choice of constants. Okay, so I've just literally formed a linear combination out of some solutions which I already know. And I'm going to choose my constants in such a way that they do satisfy these initial conditions. Okay, so I have already kind of dealt with this in one of my videos. Okay, so I know that a constant, let's say c1, is going to be my I've come up with a formula for this. It's going to be y0. Okay, so y0 is my 1. Okay, in this case, so y0. So actually, I'm going to call it slightly different. So I'm going to say my first constant. Let's just call it a general constant 1. So constant 1. So constant 1 is going to be y0 and the derivative of y0, and the second, so my y2. Okay, let me just try and write this in the clearest way. So, yeah, okay, so y2 evaluated at my t0, which is 0. Okay, t0 is 0. Okay, and y2 dash evaluated at 0, and take the determinant of that, and I put it over the Vronskin, which of course is y1 evaluated at 0, and y2 evaluated at 0, over y1 dash evaluated at 0, and y2 dash evaluated at 0, and take the determinant of that. Okay, and my constant 2, similar kind of thing. Constant 2, it's just another formula. So constant 2 is just the formula of y1 evaluated at 0, y1 dash evaluated at 0, okay, y0 and y0 dash, okay, over my Vronskin, which is y0 evaluated at 0, y2 evaluated at 0, and the derivative, so y1 dash evaluated at 0, and y2 dash evaluated at 0, and take the determinant of those two things. Okay, so what do I know? Well, I know that y1 is e to the t. Okay, so therefore the derivative of y1 is going to be so y1 is equal to e to the t. Derivative of y1 is still going to be e to the t. Okay, I know that y2 is e to the minus t, and I know that derivative of y2 is going to be minus e to the minus t. Minus e to the minus t. Let's just write that out. E to the minus t. So therefore, when I evaluate it at 0, when I evaluate this thing at 0, all these things at 0, that's going to become 1, that's going to become 1, that's going to become 1, and that's going to become minus 1. It's going to become minus 1. So now I know what those are. So, okay, so now I know what all my different things are. So now basically all I need to do now then is work out what my constants are. So these are my constants. Let's do C1 first of all. Let's do C1. Okay, so these are all the ingredients. I'm going to do Y3 first. Notice just from my initial conditions, excuse me, notice that all my initial conditions, that Y0 is just my Y3 evaluated at 0, and Y0 dash is just my Y3 dash evaluated at 0. Okay, and I want that to be 1, and I want that to be 0. Okay, so that's just from my initial conditions, right? So let's do C1 first of all. Let's do C1. This is going to be C1. Okay, so I want to work out what C1 is. Well, C1 is going to be Y0, okay, which is 1. It's going to be 1, right, over Y0 dash, so that's 0 there. Okay, and then in my second column, I want Y2 evaluated at 0, so that's going to be 1. It's going to be 1, and Y2 dash evaluated at 0, so that's going to be minus 1. Okay, that's going to be over my Vronskin, which is y1 evaluated at 0. So it's going to be this, basically. It's going to be 1, 1, 1, and minus 1. So 1, 1, 1, and minus 1. Take the determinant of that. Okay, and so therefore I'm going to run out of space a little bit, but this is going to be 1 times minus 1. So this is going to be equal to 1 times minus 1. So that's going to be minus 1 minus 0 over 1 times minus 1, so that's going to be minus 1 minus 1 times 1. So that's going to be 1. Okay, so therefore this is going to become minus 1 over minus 2. Minus 2. The minuses just cancel, so therefore I'm just going to left with 1 over 2. So C1 is just going to be 1 over 2. So I can now replace C1 with 1 over 2 just from using that. Okay, let's do exactly the same thing now for C2. This is now going to become C2. Okay, and that's basically saying y1 evaluated at 0. So y1 evaluated at 0 is going to be 1. It's going to be 1. Okay, y1 dash evaluated at 0 is going to be 1. Okay, y0 evaluated at 0 is going to be 1. And y0 dash evaluated at 0 is going to be 0. So therefore I take the determinant of that over the Vronskin. Well, the Vronskin is just going to be exactly the same thing as I've got there. So 1, 1, 1, minus 1. Take the determinant of that. So the determinant of this is going to be 1 times 0, which is 0, okay, times 1 times 1, so minus 1. So over, and the determinant of that is going to be 1 times minus 1, which is minus 1, minus 1 times 1, so minus 1. That's going to become minus 2, so it's minus 1 over minus 2, so that's going to become 1 over 2. So that in there is going to become 1 over 2, hopefully if I've done. Okay, and then we're just going to do exactly the same thing now for y4. So I now know what y3 is. y3 is now that. Okay, I've worked out my constants based on my fundamental solution. So I know now my constants are my fundamental solutions because I've derived my constants from my fundamental solutions. So therefore I know that y3, and you can verify that actually y3 does in fact satisfy my initial conditions. So when I put 0 in for this, I should get 1, which I do, and when I take the derivative of that, I get half minus a half, which is 0, which does indeed satisfy that. So now I'm going to do exactly the same thing now, but for y4. Okay, so it's exactly the same kind of thing as we did before now, but this time I've got y4 is my constants k1 times y1, which is e to the t, plus k2 times y2, which is e to the minus t. Excuse me. Okay, so let's do k1 first of all. So I've got exactly the same kind of thing going on for my y1 and y2 evaluated at 0, my derivatives as well. But this time I've got different initial conditions because obviously y4 is a different initial condition to y3. Okay, so now y0 is 0 and y0 dash is 1. Okay, so I want y0 is 0, so this is 0 now. Maybe if I just replace it directly, actually. I could do that, couldn't I? And then y0 dash should be 1. Should be 1, okay. And then y2 at 0 should be 1. That should be 1. Yep. And y2 dash should be -1. Should be -1. There we go. Okay, and then on the bottom, I've got y0 evaluated at 0. So this is 1. Okay, y0 dash, which is 1. Which is 1. Okay, so that should be 1 as well. Oops. Should be 1. y2 evaluated at 0. That's 1. And y2 dash should be -1. Should be -1. Okay. Okay, so that's what's that? Well, it's going to be 0 times -1. So that's going to be 0 minus 1 times 1. Okay, over 1 times -1 minus 1 times 1. So therefore that's going to become -1 over -2. Minuses just cancel out, so I'm just left with a half. So I'm left with K1 equals a half. K1 equals a half. Now let's do exactly the same kind of thing for K2. So K2 is Y1 evaluated at 0. So Y1 evaluated at 0 is 1. Y1 evaluated at 0 is 1. And Y1 dash evaluated at 0 is going to be 1 as well. So there's 1 as well. Okay. Now I'm going to do y0. Y0. So y0 is 0. Is 0. That's 0. And so therefore y0 dash should be 1. Should be 1. Okay. And then the bottom is just going to exactly the same denominator. Is going to be exactly the same as the Vronskin. So it's just going to be 1. Oops. 1, 1. 1 and -1. Okay, so let's just evaluate this. We've got 1 times 1 minus 0. Okay, over 1 times -1, so it's going to become -1 minus 1. So therefore this is going to become 1 over -1. Okay, that's going to become -2, sorry. So therefore that's going to become -1/2. So K2 is minus a half. So K2 is -1/2. So that's what y4 is. And I know that y4 satisfies these initial conditions because I've derived my constants from these initial conditions. Okay, so what is y3 and y4? So there's my y3 and y4. I've got the constants for that. Well, look at this. This is just my hyperbolic sine. It's my sorry, that's my hyperbolic cos, isn't it? When I've got a plus, it's a cos. My hyperbolic cos. So this is cosh of t. Yeah, if you want to write it like this, you can do. You know. If you want to. And this is my hyperbolic sine. It's my sine of t. Okay. And so basically, if I take the Vronskin of this, I can verify that they are in fact fundamental. I can verify that they're fundamental just by taking the Vronskin of these two solutions. So in other words, my Vronskin is now y3 and y4 and their derivatives, so y3 dash and y4 dash. I mean, if you didn't see that these were hyperbolic sines, then that's fine. You could have just, you could just use those. But I'm going to use my hyperbolic sines and causes just because, they're there. I've spotted it. If you haven't, you can just use that, okay? And you can just use that and the derivative of that, and this and the derivative of that, and plug it in for y3 and y4, and then take the determinant, and that will work just as well. But I'm just going to take my hyperbolic. So this is cosh. Okay, this is shine. And they both depend on t, but I'm going to drop the dependence on t for the moment, just because it makes it easier to write. Okay, and then what's the derivative of cosh? Well, it's shine. Okay, what's the derivative of shine? Well, it's cosh. Okay, so therefore let's have a look at this. So we've got cosh times cosh, so it's cosh. So I'm taking the determinant now. So it's cosh squared minus shine squared. Okay, well it's a bit like I mean there's a nice identity for that. This is actually equal to 1. This is actually equal to 1. So cosh squared minus shine squared is equal to 1. Okay, and of course 1 is not equal to 0. So therefore I can say that because my Vronskin is not equal to 0, then y3 and y4 are also fundamental. They're also fundamental. So therefore I can write my general solution. My general solution is just going to be y3, so some constant, let's say constant h1 times y3 plus constant h2 times y4. Okay, so y3 is cosh of t, and y4 is shine of t. shine of t, and so therefore that is my general solution. Now notice that I came up with a general solution. So what have I done? I've had started off with my second order differential equation, okay, and I came up with a with a set of fundamental solutions. So y1 equals e to the t, and y2 equals e to the minus t. And then what I did is I said, well, I can also come up with a set of solutions that satisfy set of solutions that satisfy some initial conditions. And I've shown that the set of solutions which I just came up with, so y3 equals cosh t, and y4 equals shine t, also satisfies this same equation. So I've come up with more sets of solutions, and I've just shown they're fundamental. I've just shown they're fundamental because the Vronskin is not equal to 0. So I've just come up with another set of fundamental solutions. So basically, what can we say from that? Just because they're basically what it means is just because they're fundamental, just because I come up with a set of fundamental solutions, does not mean that they are the only. It does not mean that they are the only set of. There's not only one set of fundamental solutions. You think that sometimes, fundamental solutions. Fundamental just means, I think fundamental sometimes get confused with unique. Fundamental is not unique. Okay, so basically what we've said is that we can come up with, in general, there'll actually be an infinite number of solutions. Okay, and those solutions, and actually there'll be an infinite number of fundamental solutions. So fundamental solutions, just because a solution is fundamental, a set of solutions is fundamental, does not mean that they are the only set of fundamental solutions to that equation. Okay, so fundamental does not mean that they are the only set of solutions that are fundamental. Okay, so if I came up with those, then you could be forgiven for thinking that they were the only set of solutions that were fundamental. But that's simply not true. These solutions are also fundamental. And in general, there will be an infinite number of fundamental solutions. So what we were doing in this video is coming up with a particular set of fundamental solutions based on some initial conditions. So in other words, you get given some initial conditions, and therefore that allows you to find a particular fundamental solution. It's a bit like going into a shop. You go into the crisp aisle and you want to find a particular type of crisps. Okay, so you can have an infinite number of crisps, but you want to find and they correspond. The analogy being that the crisps are the fundamental solutions. Okay, and you want to find the particular type of fundamental solution.